Hello everyone, and welcome to the second video in our Linux Kernel Exploitation series. After setting up our testing environment, the next step is now to reverse engineer the hackme kernel module and to see if there are any vulnerabilities there. So let's start. First, let's check the file type. When we run the file command against hackme, we see that it's an ELF 64-bit Little Indian and x86 architecture, and it's not stripped. Not stripped means that the symbols are still in the binary, and that makes our reverse engineering easier. Also, we can check the security features enabled file hackme, and this reveals that only canary and no execute protections are enabled by default. These features mitigate against certain types of attacks, but they don't guarantee absolute security. Okay, now so we have an idea about this kernel module, so let's bring Ghidra. Of course, you need first to create a new project, import the hackme module, ask Ghidra to analyze it, and after that, here in the functions window, we see the names of the functions inside the kernel module. From the names of these functions, hackme release, write, open, read, initialize, it somehow indicate to us that this is a standard character device in Linux. Let's go for hackme init here, and we see inside hackme init there is a call to miscellaneous register, which is a known function in Linux kernel to register a character device, and it receives hackme miscellaneous as a parameter. When double click on it, we see here in the assembly window that this is a struct miscellaneous device struct that has a different field, the minor number, the name, hackme, file operation. This is pointer to those file operation, the open, the write. Also, we can maybe check here miscellaneous device. You see that this is the struct miscellaneous device, and this is the names of the all the fields it contains. So that tell us again that now the hackme modules start a character or register a character device inside the Linux kernel. Let's verify that. We go to our testing environment here. First, let's check for all the inserted modules. So let's mod, and we see we have hackme already inserted here. Then let's check list-l dev and hackme. We see we have a character device, read-write for all the user. So that's mean now we can communicate with the hackme model through this device. We can read, we can write to it. Okay, now let's analyze another function. Maybe we can start with where is this? Okay, with the functions with write. Okay, so this functions receives user data and its size, user data size from user space. After that, by the way, you can see here the canary. Now we already know that the canary is enabled, so this is inside the function. After that, the function checks whether the user data size is larger than 1000 hex. Hex, that's mean 4096 decimal. If it's larger, then it triggers an error and the execution halt. If not, it continues until reach the function copy from user. This is another known kernel function that it copies data from the user space to the kernel space. So hackme buff here, this is a buffer or global buffer inside the kernel space. If I double click on it, you see its size 4096, and that's the reason why there was a check here against hex 1000. So this is the size of the global buffer in the kernel space. This function, the copy from user, it returns 0 if it's a successful copy operation, or it returns the number of bytes which couldn't copy. Now, if bytes failed equals 0, successful copy operation, then we go inside this if statement and memcopy is called. Memcopy will copy the hackme buffer to the right buffer using user data size. Do you see the issue here now? Because here the vulnerabilities happen. There is no check that the user data size is less or equal than the right buffer. Remember, the user data size is controlled by the attacker. So here, the right buffer is an array of 32 member of int. So that means 32 times 4, because int is 4 on a 64-bit architecture. That gives us 128. So there is no check now that user data size is less or equal this 128. That's mean now we have buffer overflow here. So simply an attacker could provide a larger data size, which allows the attacker to overwrite adjacent memory on the stack. So now we know hackme write has a buffer overflow. Let's check another function, which is hackme read. By the same analysis, it received user data and user data size here. At line 24 here, again we have copy to user. This is again another known kernel function. The difference is now it copies from kernel space to the user space. So from a hackme buffer to the user data, again using the user data size, without checking on how much data we could copy. So that allows an attacker to read arbitrary number of bytes on the stack. So now we have a kernel module, hackme, which runs in kernel space. It has two functions, hackme read and hackme write. The best part is neither of them checks for the bounds on data moving between kernel space and user space. This is a huge opportunity, of course, for attackers. The big question is, how can we take advantage of these two functions in order to escalate our privilege? Remember, here, ID, we are standard user. So how can use these two vulnerabilities or two functions in order to escalate our privilege from a standard user to a root user? And also remember, we have to beat the canary as well. So there is a canary protection here on these functions. So this is also something we need to consider. Think about it, experiment with it, come with some idea, because in the next video we will go deeper in this attack. So stay tuned for that. For now, thank you for watching, and I see you in the next video. Ciao, ciao.